Hi, so I'm sure you've seen this, but it is kind of cute and very relevant to generators, so I'm going to show it again. If I take some magnets and drop them, they fall into my hand with quite a speed. If I take a copper pipe and put those same magnets in there and drop them, they're very much slower. This slows it down because there's two things that happen here. One is, as we know, you pass a copper conductor across a moving magnetic field, which is what the dropping magnets are. Oh, you create a current. We've turned it into a generator. But we know from motors, if you put a current into a conductor, you create a magnetic field. So we're both creating a current in this by changing the magnetic field and creating a magnetic field in this by creating a current. Those two oppose each other. Now, I hate the idea that laws govern something. I think laws describe something. So that situation is described by Lenz's law. When you drop a magnet through a copper pipe, on the one hand you create generation. It creates the flow of a current around this circuit, which is the copper pipe. That flow of current creates a magnetic field in the direction that opposes change. And so the magnets drop very much more slowly. So it's not that generators and motors are essentially the same thing, they're exactly the same thing. So I've taken apart this 12-volt DC motor, and down there we've got a couple of permanent magnets facing north and south, and then we've got a rotor, and that rotor is a whole bunch of coils where it's connected to opposite sides of the commutator. So when we use this as a generator, we put a turning force on here, handle, turn it by hand, wind turbine, whatever, and we turn a conductor through a magnetic field. And of course what that does, it sets up an EMF and we get a voltage out of it. But it also does the same thing that happened here, because it creates a magnetic field within that coil, and that magnetic field within that coil does the same thing as dropping the magnets through the pipe. It creates what's called a back EMF, an EMF in the opposite direction, and of course that creates a counter torque. As we try to turn it, we feel a force trying to turn it the other way. And of course, in order to turn it, we have to overcome that counter torque that's the result of the magnetic field that's been set up in the wire that we have just created by turning it. Okay, we're going to leave that for a second and have a look at this. What I've got, it's really simple, eh? It's a light bulb connected to a power supply because it follows Ohm's law, V equals IR, as so many of these things do. That is a filament lamp, so it's nothing more than a resistor. When a resistor gets hot in a lamp, of course it glows, which is exactly how it works. So it's just a resistor with a power supply. Now if I put on half a volt onto that, there we go, absolutely jack. The reason for that is the resistance of this is too high. We need to overcome the resistance so that we can get some amps to flow. So if that resistance is too high and the volts are too low, no current's going to flow. We need to bang that up to its rated voltage, happens to be about 6 volts, so we turn that up to 6 volts. Presto, we get a brightly glowing lamp, which is no real surprise because now we've got enough volts there to push against that resistance, and so the current will flow. Now, how much current is flowing is just V equals IR. So volts divided by resistance is going to give us our current flow, and it's fixed by that particular circuit. That circuit draws the amps depending on the volts and depending on the resistance, and that may seem a little obtuse, but that actually is key to understanding such a lot of things. So what's the takeaway from that for our generators? Well, there's obviously a minimum voltage that a circuit is going to need in order to run. Below that voltage it can't overcome the resistance and it can't run, so it must reach a minimum. And one of the reasons quite a few things like starter motors, for instance, are such appalling generators, so it's just not that much length of wire, because remember the voltage is directly related to the field strength, the speed at which it turns, and the thickness of the wire. And you just can't turn a starter motor that fast where you can overcome that lack of length of wire. So there isn't that much length in there. The voltage tends to be extremely low, and so you don't reach the minimum required. So there can be a minimum required to actually do something. And if what you've chosen doesn't meet that minimum voltage output, it's not going to do anything. That's one of the reasons why it's kind of cool to rewind a generator with more length of wire, which is going to be thinner wire just to get it in the same physical space, okay? But more length of wire is going to up that voltage until you reach the minimum voltage. Now, the question very often asked is, well, what amps is flowing? To be honest, if you know the voltage and you know the resistance, then unless you haven't studied your Ohm's law and you're putting it through a resistive load, you know what the amps is going to be. Just calculate it. Pretty simple stuff, really. But those are the requirements. Now, amps will continue to flow through that circuit as the voltage goes up. More amps will flow, and we know that a generator is related to the speed. So if we turn it faster, we get a higher voltage and therefore more amps. Now remember, the higher the amp flow, the greater the back EMF, and so we get a greater counter torque, and so we have to put more effort in to actually turn it faster, which is why they have limitations on them. It's also, like I say, why when you choose a motor with thick wires and not very many of them and you turn it at a slow speed, you don't get a great result. Now, I've got a couple of examples of motors that are going to do this job here. So this is a pump motor from a washing machine, and actually it looked like that to begin with, and I chopped it out to the bare coils and the magnet. All that's in there is a magnet that's magnetized north that way, south that way. Pop it in there, we've got a couple of steel blocks, and then we've got a couple of coils of wire with massive amount of wire, very, very thin loads of it. This is actually very reminiscent of a generator called a Manchester dynamo. What we've got here is this is a pump from a washing machine, and it's effectively a brushless DC motor. Again, we've got a magnet in there magnetized north and south that way, and then we've got a whole bunch of very finely wound coils. They're not as fine as this one, but they're still finely wound. So if I connect up my little washing pump motor and stick the magnet back in there, I mean, this magnet's really weak, okay? We give that a spin, and it's turning around about 300-400 RPM. There we go. We can get that lamp to actually light. Now, it's not lighting particularly well, but that's actually because I'm not turning it particularly quickly. That magnet is particularly weak, but we have a massive number of turns here, so that's giving us the voltage we require in order to push enough amps through this to get that to light a little bit. So this represents a fixed power that I'm putting into turning this. Now, as I turn this, then remember, it pushes back, does work on that load. This has to overcome that. It doesn't spin at a constant speed. It actually gets slower, even though the power here is the same. If I want to make that generate more, I have to put more power into turning this in order to overcome that counter torque that we're talking about. That would make it spin faster, that would put the voltage up, and that would make more amps flow. Equally, that will put up the counter torque, and we'd need to put more power in to get this thing to spin even faster. Of course, we have a limitation. This wire is really thin. If we try to put too many amps down that wire, of course it's just going to get hot and burn out, and that represents a limit. Now, the reason I focus so much on these multi-turn coils of thin wire is because it tends to be what we're doing is using low power sources. There isn't much power in some of the sources that we've been using, and we want a usable voltage out of it. So spinning that with lots and lots of turns of wire will get us a usable voltage. That usable voltage can then be translated into current flow. But remember, when that current begins to flow, it will set up a counter torque, and so it will slow this down because it's pushing back on it. And our push on that needs to be greater than the counter torque in order to be able to turn it. Only really talked about real power, as opposed to other things that are coming on generators like apparent power, reactive power. But we're only using resistive loads, and it certainly should help get hold of the fundamental concepts of what a generator is, how it works, and what considerations are important when thinking about designing or modifying a motor to become a generator. Because you can modify motors if they're giving a poor performance for you, either by making the magnet stronger, by putting more turns, more length of wire on there, or by spinning them faster. If you do any of those three things, you're going to improve the output of them. But don't forget, it's all about the power you put on here, because this thing will push back, which is what that feels when it's trying to turn. So it's all about what you put on there. This is all about fiddling around with those three things. Anyway, I hope it was of interest. It's the final one I'm going to actually do on generators for a while, I think. I hope it helped to really get to grips with what a generator is and how it actually works. Thank you very much for watching, and please remember to like and subscribe.